Welcome back, guys. So this week let's just start. So last week we've been trying to get the initial setup for how to connect with the Virch.io. So we start off with the interface for the Virch.io and some basic helpers. So we managed to the get a little bit of work done, I guess. So let me just give you a recap of what we did. Like overall, what we are doing in general, we have our own kernel, and we want to add a file system layer. And we started off by looking into how we can implement it, and we went into the X4 file system, and we started looking into how the entire parsing works. We managed to get all the information for the file system layer, but then we learned that we also need a block layer that's below the file system layer so that it supports multiple drivers, and the VFS layer can just call the block layer functions, so we don't have to implement every driver level implementation inside VFS layer. That is what this which IO layer is going to do. No, that is what this block layer is going to do. And when we started with the block layer, we realized that block layer can also internally have multiple implementation specific stuff, and currently we are going to only support Virch.io. And we started off looking into how Virch.io works, so we just kept on going inside, and finally this Virch.io is going to be the final layer. I guess we don't have to go any further below this, and everything else should have been already implemented by Camus, and we can directly this layer is going to be directly talking with the Camus. So let's just see where we left off last week. So the flows that we prepare requests, the block number, read the right flag, we update the descriptor table pointers, change the descriptors, get the index, and we put that into the index, and we notify the queue. Okay, fine. I guess I am able to recall a little bit of what was happening. Yeah, last week we were also going through all the flags that we might need, like the one specified in this particular documentation. It's which V101 specification, and we were going through it. In general, we were also getting help from here. Where is that? Okay, closed it, I guess. Yeah, but in general, we were able to find some of the codes that we might need. And okay, I guess we can start off, but right now I don't remember exactly what I left. Did I write a comment anywhere? Yeah, we also managed to finish the DTD layer, so that is over. Is there any comments? Okay, so now it feels like a fresh code for me then. That's going to be annoying. What are the steps? I guess there must be something here that we followed, some sort of algorithm. I remember it. Wait, it must be here. Must be in the top. We don't have to go deep into the documentation. It must be in the top. Okay, forget. Wait, it should be in this one. Wait, this is the device operation. Hmm. Okay, I don't know where it is now. It should be here somewhere. We copy pasted it. Moves this the logic from there. Maybe I'll just check for this line. This looks like we copied from here. It's not here either. Shit. I guess we'll have to go with this. Okay, we have the which queue structure. Within that, we still have to define which queue description, which queue avail, and which queue used. So let's just write a to do. If not, it's just be so fucking hard. So it's going to be true, and we have to write. What do we write? We write create all needed structs, and then let's think about. I think we'll first finish this first of all. We need the virtual descriptor struct. HQ descriptor. It's here. It has an address, it has a length, and it has and it has flags. And we have next. Okay, we were also thinking about writing a helper function for converting all these things into actual C functions, so we can just call them directly here, something like that. Okay, but let's right now just put struct which queue descriptor, and it's going to have LE64, that is Little Indian. Okay, what's the default format for us? We still have to figure out that part. Yeah, this one. Convert event 64. Okay, wait. What is the default NDNS for event 64 norm? It's Little Indian. Yeah, norm. Explicitly specified, it's always little Indian. So if you want to convert little Indian to big Indian with 64. Would it be available for everyone? I guess we are using Clang and it's not a standard library function, so I guess we can use that. But in our case, it is fine. We have little Indian already, so let's just say if we want to convert it, we'll call we can call it as define, or first of all, is it let's just double check. Standard lib. Let's see. Will this be available? Okay, so it's compiler. Okay, so ARM has this instruction. Okay, I think then we can just use that. Okay. It's first of all, let's try to use it. Let's see if it is available. And okay, it is available. It has found the signature somehow, so probably it is available. Okay, fine then. Let's just start this. Int 64. And 64 area, and int 32. Length. And what is this markup of first continuous? Well, next field. Yeah, we'll think about that later. If it fucks us, we can get back to it and fix it. But right now, let's just put flags. And UN 16 next. Okay. Now we have the. Now we have to use avail. Buffers to the device. Each ring entry refers to the head of the descriptor chain, so written by it. It starts at 0, increases and refers. I still don't understand how this will be useful. I've never seen this pattern. I mean, I have seen this pattern based on if definition because, based on certain struct fields will only be compiled if a certain definition is set. Okay, that makes sense, and I've seen that pattern before. I don't understand what the fuck is this. You just define something inside a struct. Does that mean if this struct is available, this fucking definition will also be available? What is this pattern? Like defining something inside structs. What is that? Struct to have an array at the end whose size is determined at runtime. I didn't ask you that fucking thing. I know about that. Not that. I mean, which queue. Oh, fuck me. Tells the device not to. Oh. Why is this? Why did we define this inside a struct? Oh. Okay. So this definition is used by the structures within it. Okay, so this is used by this. I know. Okay, probably we can leave that. We can just write whatever we can comprehend. Structs this queue and val, and it should be uint 16 flags and another uint 16 idx, another uint 16 ring without size being defined. Another uint 16 used events. What is that? What? Brackets. File error. Is that even a thing? Oh, fuck me. GDB on God bolt. Will it compile in time? Okay, it's not VI. Return 0 and struct here, struct test int tests. Oh fuck me, I can't test struct test. Is that possible? Is that possible? Fucking hell. Why do I keep on pressing? This does not help me anyway. GDB on see, it's saying fucking error. A flexible array member in a struct with no named members. What the fuck? With 2. Then it fucking compiles. Flexible, what the fuck is that? Array number C. Oh. Okay, so you can have a last member with flexible size. Because anyway, the last member is the next structure. I mean, like, only if there is another field after that, it'll be hard for it to make it flexible because it might overwrite the next field. But in this case, it might work, but now in here it didn't work. Okay, it fucking worked. Why? Okay, so compiler has to have 2 fields. One should be, what if I put something else here? into char. So if there's two variables, two types, it's fine. You can have whatever you want inside it. Okay, interesting. As long as it's not one, it works. Okay. Okay. So in our case, we'll just have to probably wait a minute. And how the fuck did they define it? They have defined it aft as before. It's like third field. There's a field after it. How the fuck that would work? No idea. No fucking clue. And then let's just move it to the bottom. Now it works. But why the fuck did he give it here then? Maybe he asked us to put the queue size here. Okay, maybe it was supposed to be defined by us then. Okay, then I'll put a queue size of 1, 2, 48. Okay. Now you have to define the next one, that's which queue used. Almost everywhere it's the same pattern. It says queue size. Maybe it's supposed to be defined by us. That's why they have given it a comment. If not, also we learned one thing. I mean, at least I learned one thing, is that we can have it something like this. I know something like this works for inheritance too. In C++ you have classes and multiple classes, can child classes and stuff like that. You can also have the same thing in C. You just have to use define, and in all child classes you make sure you put the same order of the initial parent fields, and then you can write the other fields below it. That would be mimicking, I mean, like in general, even in C++, the compiler is going to do that for you. In C, you can do it yourself. I learned that recently too. So this is new. I mean, like, this makes sense. This only works because this is the final field, and you can have it as dynamic, because as long as you don't initialize it and override it, because maybe once you have initialized it with some dynamic output and it is stored somewhere, and the next after that memory layout, let's say it used 50 bytes, and the next 51st byte might be used by some other structure. So at this point, if you try to override with this data with some extra data, you might actually overflow the current location and overwrite it. Yeah, that's the only issue. But okay. No, let's just write the used part. Instruct which queue used is u in 16 flags and 16 idx. First of all, which queue needs which descriptor table and which queue avail, and we have some padding, and we have which queue used. And, let me just recall why we have all of these. Because from what I remember, the which queue is just a memory mapped register, and we have multiple fields after it, so we can only say that the descriptor starts at this location. I think we say that in this low and high, and avail low and high, and used low and high, and anything, and within that, so we just give the starting addresses for all the locations. Like this descriptor, we allocate it somewhere and give the starting address inside that register, and then within this descriptor we actually put in the, we chain multiple descriptors and we put in the index into a different register. So in general, almost everything is allocated in a single location, and we put in those descriptors into those allocated location, and we just give the index of that to a register that is defined by the which IO. I don't know if it makes sense, because even I got confused last time, because the overall structure did not come into place. But now I do get it, because it's just that which IO has registers, and we manage all the memory in our side. We allocate everything and we pass in the locations to those registers of which IO. Nothing much. Okay, so we have it. We also have the way used. Okay, first of all, what the fuck is this? Paths. Do we need it? No, I'll think about it. What is which use element? Okay, so it is written by the device and we read by the driver. Okay, you can also define that then. Struct which queue used and you can have it like event 64, event 32 ID, and event 32 len, and okay, that should be good. Okay, so we have some structures and we have some helpers. Inside K-main, what are we doing? Okay, inside K-main we allocate the which IO structs. This is the main struct that we might need. It's just going to have a which IO base, because there's multiple which IO mimos that I saw in my thing. That's why I made it like this, because if not, initially I was trying to hard code that address. Now we can just store it inside this which IO, and we whatever we took from the parsing, this is the information that we took during our parsing stage. and we store that as the virtual base, which will be our base register for this x4. And then we create a new queue is of which IO queue size, and then we pass both the object and the queue to initialize which IO driver. And now we have to implement this function. So I think we saw this logic somewhere in this documentation. Now I'm not able to figure it out. Let's just check for reset. This is it. Reset the device. So we start by updating the status to reset, and update status is just going to write this register, which is virtual status. And then the next thing we do is acknowledge the status by saying the guest has notified the device, notice the device. So we are saying that the device has been acknowledged. Let's start doing some stuff. And the driver status bit. So now we also have to say that we know to drive the device, and we have to set that. I think because maybe there are some other steps we can do, because they have introduced this flag. For some reason we might have to wait and then we notify the driver. It's possible. And then what we do, we collect all the features, possible features, and then we set features okay. I'm just directly setting features okay because I'm not going to read anything. I'm just hoping my device should have all things that I'm expecting. We can maybe write that later. And then we have the read device features. Okay, that's done. Okay, so it's read device status. Okay, I'm not performing these two steps. I'm just directly setting driver okay. Okay, fine. Not sure if it will work, but we can try. Yes, I think now we'll get one. What is that? We'll get an translation fault because this address is in some other region and that's not yet mapped. Let's just see it in action and then we'll map it and then we'll think about the next steps. Why am I in Claude? Why am I having Chromium? Okay, I guess I'll just put bash builds. What the fuck? File not found. Drivers which I have bulk, drivers which I have bulk, which I have hedge. That is all. Driver which I think maybe I'll have to add it here. Okay, it's possible. Or maybe it's just because it should be a linker error, not compiler error, unless it did not find the actual file. Kmain.c. I think we have to go one step back and we have the drivers. We go one step back. Yeah, and then we have the drivers. Yeah. Okay. Now we have better error message. Now what are we trying? Incomplete field struct used. Forward fucking declaration. That just means that we did not define it properly. Only which IO is a type def. Everything else is just struct. So we have to use this. It follows the error. It's incompatible integer to pointer conversion. AK struct. Okay, it says underscore, so it's type deft. Probably that's why. No, I just have to put. No, I just have to put this here. Holy fucking moly. Why is it not working? I think we put pitch IO star. That should be good. And here we can put which Q star. Which Q is not typed of, so we can use drop. Okay. Hey, now what's the issue? Oh, it's a fucking linker error. Then probably we just need. You just need the header files. Wait. We have linked it, and it's just the header. Headers should not cause. It's just header. Even if we get some implementation error, then we might have to actually link it. But here it's just header. It should not give me a linker error, right? Which Q used, so it's actually probably the reason is that we have defined it here. Okay, let's just delete it and put it here and lift it. No, I think it should fucking work. Okay, now we have an actual linker error, and it's just saying you have referenced something but I don't see it. What the fuck, bro? So now we can actually give this here and say drivers slash which IO slash which IO blk.c, and you can say which IO blk.o. What the fuck? Okay. What? Cannot open. Cannot open. Oh, which you underscore blk. Okay, we have it working. And as soon as we come here, we should expect. Let's just remove that camo file. It's going to have thousands of. Let's just put it here and kill it and say camo. Okay, because I don't have it anymore. Camo 1. Oh no. Need grep AI and let's grep for far. Okay, you have it. Let's just put 10. Okay, when we try to access A46, we got the thing and we try to access it from EL1. So yeah, we are in EL1. So, and it is valid because if you come back to our thing where we try to wait, why is it not printed? Where's the result? That's not right. We should be breaking here, not here. We have as a name. Oh, okay, it is here. It is here, it's here, it's here. It's here. And if you copy that and go into this, and I guess we have already typed it here, we just copy it, and it's A00. This is the MIMO address that we are trying to read, and now we'll probably have to write that, add an table entry for it. So let's do that. So we can add it into, wait a minute, I think we did change something like that. Okay, we have to create the table entries here. And it should be in EL1's register, EL1's table. So we don't want to map that to user table. That's not needed. We just have to map it to, we can map it here. think I'll just copy this and I'll write a helper. It's going to be void at which IO page, and it's going to take a event 64 value rich, and it's going to just have these implementation, and we can put an event 64 here, L2 des 2. And we can put right directly here. It's in a completely different. No, we have to calculate the index for was it the one that we are going to define now, and it's going to be define is it which IO register range, and it's going to say take something like this, but a little bit away. Eight six. Let's just choose 8.6. And we can copy that. It's going to be which IO reg region. We want to calculate index for L2. Okay, no, I get it. U and 64 T, and this will be IDX. So we calculate the index for this virtual range, and we map it to the register, which will be the one that we got from the DTD parsing. So we map this to whichever register range that we got here, and it should work technically. I think so. We'll see. Let's just copy this, and but the issue here is that if we are going to hard code this range again, then we can't have multiple MIMOs, because I think because here we are trying to use this entire thing because we want to use multiple which IOs, and everything will have its base address inside it. But currently we just hard coded the base address. Fuck it. This is hard coded to what? Where the fuck is it? And it's hard coded here. If we need it, we can change it later. Let's just try to move past this because it's let's just get something walking first of all. Now we have to just copy this. Can we sit like this here? Extend. Okay, we can do that. I didn't know that. Let's just see. And then we have to map. What the fuck did I paste? Add the child page. Just call that with drive info 0. Now we have the mapped thing. Now we can just directly use which IO range here. Okay, that should be fine, I believe. I think, can we call it from here? Because those address ranges, do I even have the page entries for this, for reaching this particular, what is that? These three things, because I need to reach this now, and this fucking thing, I don't know if I even have table entry for this. Well, let's see. Oh, guess we don't. We don't have a... So what was the error? No, we don't need to put tail. What was there? Tail 100. Nope. Tail 500. Oh, let's just see. Looks like there's no error. Where should we actually finish? Wait. Printf test unit done for virtual driver. Oh, let's just put fuck me. Oh shit. Okay, so we did initialize it. So we just stopped at our while loop. That's just, I don't know, I didn't think it would work, first of all. Okay, interesting. I really didn't think it would work. Now it feels suspicious that why it works. Okay, in case I have all those table entries. I was able to reach it, then I have to, okay. Fine, whatever. Now let's try to actually read from it. So we have to, now we have the, this is right here. We have the location mapped. First of all, I don't think I can say that it's mapped because I haven't tried to write to it. Only if I try to write to it, I know if things break or not. Okay, yeah. So let's just simply, no, I did try to write to it because I am updating status here. Okay. So now let's just see how to prepare a request to write to block 100. Prepare all descriptor table values. Okay, we have to do two things. Now let's see how we can prepare it. That is it, right? Because this is how device initialization works. And then we have the device operation. We don't care about most of the stuff. Right now our example is supposed to only write a small thing into block 100, nothing much. We don't even care about if we manage to properly keep track of all the blocks and stuff, anything. We just simply want to write let's say 50 bytes into block 100. That's all we need to do. Okay, this is the which queue configuration. Probably we will have to do, as a device can have 0 or more which queues. For bulk data transport, driver is to configure them. Okay, then let's just define this which queue. After that, we also probably have to define this part. I think we don't have to do this. We'll think about it later. No, we have lots of stuff. I think this is what we have to do. This I don't know why they have mentioned the same step like multiple times, like how to configure a queue. But right now, let's write that part. We are going to configure a queue. Initialize void init queue, and it's going to take a which IO object obj. Okay, fuck. Just give me the steps to actually define I guess we have the descriptor here, so I think all we have to do is that set these values and first of all initialize the queue and prepare this descriptor and put them into this avail. I think that is all. First of all, I guess we initialize these three queues, these three things somewhere, and put their addresses into the registers. Okay, let's just do that first of all. Instead of preparing the request, let's just let's put initialize init addresses, init what can I call it, init virtual registers. Okay, and we go which objects. And right, which are registers. We have to define allocate memory for all three types and put them into the registers. I know that's how I remember it. Let's just double check it. Prepare the request, update the set type. This is prepare requests. Add to avail ring, write a index of first descriptor to avail ring. So first of all we need to define the avail, define the descriptor. First of all we need to register all of those things into these addresses. Let me just double check that. So wait. Init the driver, I guess. Now to allocate. Okay, so now to allocate space for the descriptor, which descriptor, which avail, and which used, and write those allocated addresses into the which IO registers. Example q dis low, q dis high, avail low, avail high. Am I doing the going in the right direction? Allocate the memory for 3 virtual queue parts. Enchum is physically contagious, that is they are 4 KB aligned. Okay. And program the device registers. And physical page frame number of allocated memory 2. What do you mean physical frame number? Now I'm inside DL1, inside kernel VA. So do I allocate memory and send even if I allocate it, how do I know? Allocate the memory in kernel VA? Or should I allocate physical memory? But how come EL1 has access to kernel range? I mean, that was a stupid question, but I meant like how exactly do we know which physical, because we are doing all our stuff in kernel and we keep track of things in physical things, in physical ranges. Still, if we want to directly pass a physical thing to this which IO, allocate physical memory. Yeah, they'll give me a kernel virtual address, convert them into physical address, and okay, I didn't see this step anywhere. Okay, so I just allocate them and I convert them back to physical. So in general, we are just we somehow need to know the physical address. That was my question. It's not about how I'm going to allocate it. I just need to know that these are the physical locations that are going to be used. And the virch.io will directly use the physical address. We as a kernel from EL1, we can use those physical address through our virtual range. That's why we need the mapping. So we need to call it through kmalloc, because from our virtual space, we cannot access the physical range. We'll have to allocate it through kmalloc, convert and get the physical range, and pass that physical range to... Oh shit. Allocate. Where the fuck is that? Allocate memory. All three stocks. With kmalloc. And get the physical range for the allocated VA. In our case, there is this identity mapping, so we don't really have to do anything. And pass the physical address to whichever. So we need to do it this way. Okay. In that case, maybe you could just that case, let's just take this, paste it here, so we can allocate everything internally, and we are going to have event 64 pointer. No, just event 64. It's going to be a physical address of physical which queue, and event 64 physical, and this is going to be which queue avail, and 64 physical which queue used. Okay, so we need 3 physical addresses. So we allocate them and we store the physical addresses directly here, so we can later on just use them and we don't have to do the allocation within this file. And we can do the allocation here. Yeah, I think so. And now we need to do 3 more allocations. which should be just copy fucking thing and paste, and this is going to be one of it, and this is going to, and we are allocating everything as contiguous space. But are they 4KB aligned? I don't know. They may not be allocated. It's easy. What I can do is that I can allocate, let's say, 4KB random bytes and get the address. If the address is not aligned, I can just add the extra bytes as a new alignment. So it's like this. What I do is that I have the address of this and I know the size of it. Now I have to check if the address plus size is 4KB aligned. I guess if it's 4 divided by 4, it should be good, I guess. Yeah, let's try. UN64 current padding equal to which UN64 which IO object plus size of which IO. Now I have the current location of the what is overall has been achieved, has been used, and if that number is not, I can just get the reminder. If the reminder is not 0, I can just allocate that reminder as actual space. Am I allocating? Okay, yes, I just remembered it. I am allocating everything in terms of 4KB pages. Even if I allocate this, even if I allocate some random memory, it is still going to be 4KB page. I think so. So I think I don't need this. I think my pages are already 4KB, even if I try to allocate something less, it would still allocate the full 4KB. It's not efficient, but maybe come back here if something goes wrong. Okay, and let's just put these here, and we have to allocate which queue, and it's a struct, and we have struct which queue avail. I think we have to which queue descriptor, which queue avail, and which queue used. Okay, which queue used and which queue avail and which Q descriptor. Okay, hopefully. I tried to do something, it fucked me up. Which Q descriptor and which use struct, which Q avail and it's used. Oh fuck. Wait. Okay. Okay, should be good. Now we have 3 things that are allocated and we need to convert them back to physical. I think I just have to remove the upper bits because it's identity mapping. I can do that directly. Can I? How do I convert something to physical? Now I have to convert something to physical. What do I do? How do I do it? I need the upper bits gone. The upper bits are not needed for me. I guess there must be some helper here because I know I did it already. Must be MMU. I don't see it. Okay, whatever. Whatever. Let me just say we need FFFF gone in the top so we can and it and with 000 and FFFFF, so the upper bits will get, and if both the things are, I think I tried this before and I fucked up lots of times, so okay, it's fine. Let's just write even 64. I think we can just write define convert to physical. And it's going to take What is going to take? But it's happening in runtime. Oh fuck. Okay, then I'll put static inline even 64 convert physical, and I put it will take even 64 at, and I'll say return 0x1234 123. No, I have to put 1234 1234 1234 1234. I guess it's correct. 134. So this and now it should keep all the lower bits as it is and just remove the upper 4 bits as 0, and that's all I need. Hopefully I'm not fucking up this, because previously I have tried this several times and I always fucked up somehow. Okay, it's time for a little Emacs. Shoot. Got it. And with and cut it and cut it. Okay, after 1,000 years I have managed to do one thing with this, and I guess I have to write specific things anyway, so fine. It's what I have to do, put here, it's which IO descriptor object and which IO avail object and which IO used objects. Okay, I have 3 objects. I have to write them into which IO objects. It is physical avail. No, descriptor. What the fuck did I write there? DSC. And we put it here. And let's just copy this whole thing and put it here and paste. Put it here and paste. And used. And with Q and Q here. Okay. Queue is fucked here. Okay. Now we have the virtual base and we have 3 physical addresses that are allocated. Hopefully in 4K aligned pages. Now we could just simply hope that everything works. Well, I guess it should work. Well, at least we haven't done any actual implementation. We're still setting up stuff. So let's just put some to-dos. Allocate the 3 memory. That is done. Now we have to write the lower and upper parts separately into the registers. This is what we have to do. Okay, I will do that tomorrow then. Okay, today we managed to actually write a little bit of helpers, and in general we managed to, I guess, set up the registers and set up some, also map the page table entry for our MIMO register, base register, and then also we have allocated all these 3 values, and we also confirmed that I guess this is the step that we need to take, because even from my understanding I felt like once we are done with the initial driver initialization, we'll have to just allocate all these 3 things and pass those registers into the actual which IO registers, pass this address into which IO registers, and then we should be able to create a request, which would be the request class that we have. We do have a request class, and it's this. And once we are done with this register class, we can actually start with the write operation and see what happens from there. I guess that's it, guys. Thank you. Have a good day. Bye.